Hello everyone, good evening. Welcome to the course of Defects in Crystalline Solid Part 1. So in this course, this is a 8-week course in NPTEL in which you will be introduced to the basics of what is a crystalline solid and what are the defects in a crystalline solid and how the defects result in a good or a bad way in the crystalline solid. We are going to look into this in this course. This is taken by Professor Shashank Shekhar from IIT Kanpur, and I will be the teaching assistant for this course. This is the first session as for the tutorial of this course, and in this first session, I will be first introducing you to the crystalline solid, and then I will be introducing you the defects in the crystalline solid. We will be discussing just one of the defects in this lecture. Then further, as the course progresses, we'll be discussing multiple defects and its effect on the crystalline solid. So let's begin our course. And about the doubts, if you have any doubts, you can ask me in this session, or else you can drop these doubts in the drop box so that we will be answering the questions which you have. And all the sessions are recorded, so you can find the links to the session. If you find something interesting in the sessions, then you are always welcome to watch them again. Then what is crystallinity? First, let me introduce to you to crystalline solids because the because the name of the subject is defects in crystalline solids. So what is a crystalline solid? Let me first introduce you about that. Then I will be introducing you about the defects. As we know from our high school level that the solids are divided into two parts. One is crystalline solids, one is amorphous solids. And in case of crystalline solids, there is periodic arrangement of atoms. This is one statement which you have learned in the high school. Periodic arrangement of atoms. That means, as you can see in this 2D figure, the atoms are arranged in a periodic, repetitive manner in a 2D. You can see there is a repetitive manner of arrangement of atoms, whereas in amorphous solids there is no such repetition or no such periodicity observed. Atoms are randomly arranged in a 2D system, as you can see here. And extending this to 3D is like, in 2D we have a regular arrangement of atoms, and this regular arrangement of atoms is in x and y direction. This periodic arrangement is in x and y direction. And again, if we repeat this periodic arrangement in z direction, we are getting a three-dimensional solid. So the three-dimensional solid, as you can see here, has also a repetitive arrangement or a periodic arrangement of atoms as seen in the two dimension. Similarly, for amorphous solids, they will be randomly oriented. So this arrangement of atoms decides the property of the elements, like how closely they are packed, how randomly they are oriented, as in case of amorphous solids. This will decide the properties they will show in the bulk materials. To just give you a brief idea about what I am talking, like what is crystalline, what is the crystallinity and all. Let me just show you some videos. In this video, we will be learning about the different types of crystal structures. As we know, these are simple cubic, body-centered cubic, face-centered cubic, and hexagonally closed-packed structures. Simple cubic has atoms only at its vertices. The body-centered cubic has atoms as its vertices and at the center of the atom, the center of the crystal structure. Then the FCC has atoms at the vertices and in each of the faces. And finally, the HCP, hexagonally closed pack structure, shaped like a hexagon. Let's see. how this periodic arrangement is occurring in these atoms, this molecules. Sorry. As you can see, this is a BCC crystal unit cell, BCC unit cell, and you can see that there is an atom sitting at the center of the crystal structure, crystal lattice. This is a FCC crystal structure where the atoms are sitting at the vertices along with at each of the faces. This is the hexagonally closed back structures. As you can see, it's in the shape of a hexagon. The two surfaces are the shape of a hexagon, and each of the surfaces has atoms at its vertices, and then two atoms, one atom at the surface of each of the surfaces, as you can see. And there are three more atoms at the center of these two hexagons. As you can see here, these arrangement and these are at the bottom and the top arrangements are same, and this arrangement is quite different from that. So yeah, this was just to give you an idea about what are the crystal structures and how they are the periodic arrangement of atoms are there in the crystal structures. Um, as I said, these periodic arrangements, the randomness and how periodically they are arranged, how the arrangement of atoms, how they are occurring in the solids, determines the um, properties of the materials. So let's think of a question. If I introduce some defects in the materials, the defects, yeah, I mean, I'm adding some impurities to this periodic arrangement, or I'm creating some discontinuity in this periodic arrangement. What will happen? The properties will be changing because, as I said, the periodicity of how periodically the atoms are arranged determines the properties of the material. So, if, when we are introducing some discontinuity in this periodic arrangement, there will be an observation in the properties at the bulk level. So, what are defects? Defects are generally discontinuity in this periodic arrangement of atoms. I'm talking about defects in these crystalline solids. So for example, think of a situation in two dimension. What are the defects can we introduce? In two dimension, this is the perfect arrangement of crystals. This is the perfectly arranged crystals as you can see here. What are the modes I can introduce a defect in this perfect crystal? One method is by adding some impurities. I will be adding some foreign particles in this material. So where will this sit? They don't have exact lattice points of because they are quite the lattice points are quite occupied everywhere. The lattice points are occupied. Where will the impurity sit? The impurity will sit within the lattice points, like some of the lattice point, some of the voids which are present, the element which you are adding, external element, will sit there. So this will create stress field, strain field around that matrix, around that. So when the material is introduced here, this will create a stress field around this, because there will be a lot of change in the bond morphology and everything in this material. So there will be a lot of strain developed in this material. Similarly, another point can be, in this case we are introducing defects. Another point can be, we can introduce defects is by removing one element, that is called vacancy. So that means there is a periodic arrangement of crystal here. We'll be removing one of the atoms. This will again create a strain boundary. How? Because there is a bond change. The For example, take an example of this atom. It is attached with this atom, this atom, this atom, this atom, and in 6 ways. One, two, three, four, five, six, seven, eight. In 8 ways they are arranged. They are bonded. If I remove this atom from here, so these eight, there will be eight broken bonds here. So this will create a disturbance in the geometry, or this will create a disturbance in the strain field around here. Similarly, here are some of the examples of defects, or how can the defects be introduced in a crystalline structure. One is the substitutional atom, which I explained here. Like one atom is substituted. This is one of the thing we'll be looking onto in the later in this course. Like one of the atoms is substituted by another atom. This is creating a strain field, as you can see here. The bonds are not straight enough. Then there is a vacancy defect, that one point the atom is missing. Then there is another strain field created around here. Then there are interstitial atoms, as you can see here, interstitial atoms. This is also creating a strain field. Here also an interstitial atom creating a strain field. Then there are S dislocations, grain boundary dislocations, the grain boundaries, sorry, S dislocations, grain boundary defects. These will be discussed later in this course. Then as you can see, the pores or inclusions which are present in the sample also is creating a type of defect in the periodic arrangement. Similarly, the precipitations, they are also creating a kind of defect in the sample. So as you can see, these defects are creating a discontinuity in the arrangement of atoms. That means this will in turn affect the properties of the material, because there is a discontinuity. Even if the properties and this of the material at these areas will be uniform, because the materials are uniform, but when the properties of this material will be different, here the properties of the material in this portion will be different, because the material is totally different. Either a new material is introduced or something is absent, so the properties will be varying. So this is what the importance of defects is. Then the various types of defects. We have classification on the basis of on the basis of dimensionality. So there are zero defects, zero dimension defects. That is point defects. Like as I said earlier, told you earlier, point defects are like a single point atom is missing, a new atom is added. These are all called point defects. Vacancy, that an atom is missing at a point. This is called vacancy defect. Impurity, we're introducing a new atom or a new impurity into the cluster of atoms. This is known as impurity. So as you can see here, there is a impurity here introduced. Then Frankel defect, Schottky defect. These two defects are in ionic solids. I will be discussing about these two defects later. These are also coming under the vacancy and substitution and everything, and coming under the umbrella of zero dimension defects, but they are specifically for ionic solids. I'll be discussing this later. Then comes one dimension defect. One dimension, as you mean, here the zero dimension, that is in one point atom is missing or atom is being added. One dimension is if we increase that to a single line. If there are multiple in a single straight line, there are multiple defects, that will be one dimension defect. Like in a single row of atoms, in a single row of atoms are missing a single row of, here you can see a single row of atom is missing, a single row of atom is missing here also. These are all point point defects extended to a single row, that is line defects in a one dimension. So these are dislocations, disclinations, disparitions. We'll be discussing this later. Then finally comes two dimensions. Two dimensions, as you mean, this will be extended in this direction and as well as in the y direction, x and y directions. If I'm extending that, that will be so x and y direction. That means an area. I'm distributing the dislocations or the defects are generated in an area. That means surface interface boundaries, these grain boundaries, as you can see, this is an area to which the defect is distributed. Twin boundaries, stacking fault, antiphase boundaries, these are all examples of two dimensional defects. Then finally, x y we have introduced, then one axis remaining, that is z axis. If we introduce defects to the z axis, that will be three dimensional defects or known as volume defects. Twins precipitates, as you can see, precipitation, if we are adding precipitates here, it's a three dimensional defect. It's a big precipitate which is this figure is a two dimension figure. It's that's why it shows in two dimension, but if we extend it into a z axis, the precipitation is in three dimensional defect. Then faulted region, void and cracks, pores, these are all three dimensional defects. Thermal vibrations, examples of three dimensional defects. So finally we got to know that the what is crystalline structure, what is crystallinity, and if you are introducing defects, what are defects, and how defects will affect the properties of the material. We got to know about this. So today we will be mostly focusing on zero dimension, that is point defects, vacancy, impurity in case of normal solids, and Frenkel and Schottky in case of ionic solids. Then what are point defects? Point defects, as I told you earlier, is like only one or two atoms are missing, one atom is replaced, one atom is missing, or an impurity is being added to one place within the periodic arrangement. These are all point defects. They don't have dimension, or they are zero dimensional defects. They are 1 to 2 atomic diameters, like 1 to 2 atomic diameters in like in the area or in the length to 1 to 2 atomic diameters, because one or two atoms are missing or one atom is introduced is anything else. 1 to 2, it limits its range to 1 to 2 atomic diameters. But this effect will be felt in the bulk sample. The effect can be felt in a very large distance. These small change, small substitution, small change in the periodic arrangement can affect the properties of the bulk sample. This is what is the importance of defects. Then this is 1 to 2 atomic diameter in, as I said, 1 to 2 atomic diameters. Then but the effect is felt at a very large distance. As you can see, the examples, interstitial atom is introduced into the material. There is a creation of lot of disturbances in the surrounding elements. When the vacancy is created, there is a lot of disturbances. Then there is a Frenkel pair, which I will be discussing later. Substitutional, there is a periodic arrangement of atoms, a new atom is introduced into the place. Substitution, then substitution of smaller atom, interstitial atoms, these are all point defects, and these will affect the properties in the final bulk sample. Then one may ask you the question, like how are these defects generated? Because if we make up a crystal, it we want always the crystals to be perfect without any defects. So how are these defects generated in a crystal? The defects, the generation of, as we all know, the defects generation, as thermodynamics says, that the generation of any of the production requires the requires the requires overcoming the energy barrier, that is the activation energy barrier. So if we overcome this activation energy barrier, then these defects will be formed. So the activation energy barrier can be overcome with the help of when there is a favorable energy available. This favorable energy is provided during crystal growth, during quenching. Quenching, as you mean cooling very rapidly at a very high cooling rate, we are cooling the sample. That's called quenching. Then irradiations means we are radiating materials with different rays. These are called irradiations. Then finally, plastic deformations. These are all uh, techniques provide the favorable energy to overcome the activation energy to form this point defects. Then one may ask the question, like we want a solid to be purely crystalline. Why are we introducing defects in that material? Because the defects will affect the properties. It's like it is creating a nuisance in case of materials. Why are we adding that? The thing lies in thermodynamics. As Professor Shashank explained you about the I will not go into details about the thermodynamics of what is happening. We can also we can always go back to Professor Shashank's notes to find out what is happening, how is thermodynamic related. I will just say the conclusion, what we derived from the thermodynamics. We found that introducing defects in the material can reduce the energy of the material energy significantly. That means generally speaking, according to thermodynamics, every material or everything tries to attain a state in which the energy is quite low. They always try to attain a low energy state. So if we introduce defects in the material, the material attains a low energy state. So why will not the material be? Why the material will always try to attain that low energy state by introducing defects. And by thermodynamics, it proves that introduction of these defects decreases the energy of the material. The energy drops rapidly. So that's why finding a crystal which is defect free is quite impossible, near to impossible, because introduction of defects significantly reduces the energy. So why will the material have no defects in them? They will try to have any of the following defects in them. Then concentrating on the zero dimensional defects, that is vacancy defects. What are these vacancy defects? Vacancy, as I said earlier, is the missing of an atom. A point, like there is a regular arrangement of atoms, but there is an atom missing. There is some energy due to some of the processes mentioned in the previous slide. In the slide, due to these processes, there is a vacancy created. There is a missing atom. This is known as vacancy defect. We have a video which can briefly explain you what vacancy defect is. Let's watch that. As you can see here, this is a diamond crystal, diamond lattice. In a diamond lattice, you can see there is a periodic arrangement of all the atoms present in this diamond lattice. Then another atom immediately, as you can see in this periodic arrangement, when see when there was a proper periodic arrangement in this lattice, and whenever there is a the when the atom from a point position is taken out, there is a stress field generated. All the atoms are crushed into that, because there is a bond breaking within these atoms. That's why there is a release of energy, and there is a shift. They always try to tend to come closer to each other in case of vacancy. This is another, if another defect, that is we are introducing a new material in that. vacant position. This is known as substitutional defect. As you can see, when a bigger atom is introduced there, there is a generation of stress fields. The atoms are moving further apart from each other. This also this image also shows the same thing. There is a generation of stress field around them. So this video was just to introduce you to what is the vacancy defect and what is substitutional defects. How are they happening in case of material? Then there are different types of thermodynamical equations which are related to vacancy defects, like how the monovacancies are formed, how monovacancies, as the name suggests, formation of a single vacancy, how the monovacancies are formed, what are the fractions of formation of monovacancies. Then from mono vacancies we went into die vacancies, like how the die vacancies are formed, what is the fraction of die vacancies in the material, and how the mono vacancies and fraction of mono vacancies and die vacancies are related to each other. And even Professor Shashank explained some problems regarding this. So if you have any doubts regarding this problem, we can discuss it in this class, or maybe you can put it in the discussion forum. We can go through that. Then discussing about mono vacancies and die vacancies, we got to know about one point, that the energy of the mono vacancy is always higher than the energy of the die vacancies or any other vacancies. So that means that to reduce the energy of the system, always die vacancies, tri vacancies, or any other vacancies will be preferred more than mono vacancies. So that means that as the energy of di and tri vacancies are lower, the formation of mono vacancy is more unfavorable than the di and tri. So the di and tri are more favorable over mono vacancies. So mono vacancies will coalesce with each other to form di and tri vacancies. Then we learned about the sinks and sources of vacancies, like where the vacancies appear. These are known as the sources of vacancies, and the sinks of vacancies, like where the vacancy is gone dead, goes down, or where the vacancy goes into to goes into dead. That those are known as sinks. Then we have um, yeah. Then we have the concentration measurement of vacancies. Like how we have vacancies in a material, we have bi vacancies, we have mono vacancies, we have tri vacancies in a material, and how to mathematically measure them. Like how many vacancies do you have in a material, how to mathematically measure them. There are various techniques for the measurement of these vacancies. One is thermal expansion. As I said earlier, the vacancies require some energy to be created, and there is thermal expansion. Thermal expansion, as the name suggests, we are providing some energy to expand for the material to some heat energy for the material to expand, and this expansion is generating some kind of vacancies. But one thing to remember here is that when there is a thermal energy applied to a material, there will be a thermal expansion of the material. That is the general property of the material, that there will be a thermal expansion. Then there is creation of vacancies due to the heat energy we are providing. So that means that the increase in length of the material or increase in volume of the material will depend on two factors. First is thermal expansion, normal thermal expansion, that is the property of the material. Then with the creation of new vacancies, like how many vacancies are created, that will depend on that. And solving these equations, we'll get that the fraction of vacancies which are created is related to the change in length or the dimension of the material due to the thermal energy provided, and the change in uh, crystal lattice structure. This is the crystal lattice parameter, the change in crystal lattice parameter which you are observing. And this crystal lattice parameter can be found from the XRD results. They can give you directly about the crystals, what is the change in the crystal symmetry. And these change in length can be found from optical instruments by just observing what is the change in the length of the material. This can give you the number of vacancies created during the thermal expansion. There was a question solved regarding this thermal expansion about copper rods, where the length was given a 2% increase, and there was an increase in the temperature. And uh, the question was asked that what fraction of these vacancies is created due to what fraction of this expansion is created due to vacancies. So Professor uh, Shashank has solved that equation, and he concluded one very important conclusion from that is that the density of the structure, like it, the copper rod increased in length, but the the percentage of vacancies which are is related to the increase in length is very less. Like they don't contribute to the increase in length much or the increase in the density much. The only density decrement or increment is occurred only by the thermal expansion or the thermal heat we are giving. Vacancies do not include anything, do not involve in the density change of the material. So that means density is a structure insensitive property. That was the what was concluded from the problem. Then another point is the heat capacity. Heat capacity is given by this following equation. The solving of this equation has been done by Professor Shashank. We can go through go through the lectures to get how these solutions have been done. The It shows that the fraction of vacancies ha- depends on the heat capacity of the material. Heat capacity depends on the fraction of vacancies. These are all the fraction, these terms like delta HF1V is the fraction of mono vacancies. Then temperature, this is the temperature, this is Boltzmann's constant. Then this is also the fraction of mono vacancies. So it shows that the heat capacity is also a factor which can determine the percentage of vacancies or the how much vacancies are present in the material, that can be determined by the heat capacity. Then comes another method that is called positron annihilation spectroscopy. This is a very good technique to analyze fraction of vacancies at a very low concentration. If the vacancies are present as a very low concentration, the above mentioned methods such as thermal expansion and heat capacity, they may escape this. Like if they're present in much higher composition, the defects or the vacancies, these may be able to justify those. But when the concentration is very low, this is where positron annihilation spectroscopy comes into play. What is that method? Let's learn about that. Positron is a antimatter of electron. Electron has a negative charge and positron has a positive charge, but the mass and the density and everything is same as electron, but the charge is positive in case of positron. So what we are doing, we have two materials. One material is with less number of defects, and one material is with more number of defects. These small circles are the defects present in the material, and we are irradiating the material with positron. As I told you earlier, in place of defects means what? Vacancies are what? In that place there is an absence of atoms, that is known as vacancies. So if there is an absence of atoms at these places, that means the electron density is lower, as the atoms consist of electrons, protons and neutrons. The electrons are missing in those portions. That means if the material has more defects, the electron density will be lower in that material because the atoms are missing in that material. And as the electrons are lower, this positron, which has a positive charge, will find it easier to sit in those defects, because there is no one else to neutralize its charge. The electrons are not present to neutralize the charge of the positron, so they will be easier to they will find an easier time to sit in those vacancies. So to decay, what is to decay? Decay is the reaction which occurs between electrons and positrons. So it will be difficult for them to decay because there are no electrons present in this in the material with higher defects. Whereas when we come to the material with lower defects, that means the more number of electrons are present in the material, the electron density is more in case of materials with lower defects. That means the positrons which are irradiated onto the sample will will have less time to decay. That means it will decay easily because there is availability of electrons in the material. So this time difference, like how much time it is taking to decay and how much time it is not taking to decay, this time difference can be related to the vacancy concentration. So that is the average time decay, like how much time it is taking to react with the electrons, how much time it's not reacting with the electrons, can be related to the vacancy concentration, which is given by tau equals to 1 plus tau 2 nu cv by 1 plus tau 1 nu cv1, as discussed by Professor Shashank. Then there are these are not the only methods. There are some other methods also to determine the concentration of vacancies in a material. Those are resistivity. Resistivity, as you all know, is a material property to offer the resistance to the material, resistance to the flow of electricity, flow of thermal conductivity, everything. These are thermal flow of thermal energy, flow of electrical energy. These are all resistivity. This is all resistivity, which uh, hinders the flow of this thermal energy and electrical energy. Then known as conductivity, the opposite of resistivity is simply conductivity, like how much thermal energy and electric energy can pass through the material. These can also be determining the concentration of vacancies. As I said earlier, the vacancies in the atomic level, the vacancies which are created in the 2D and 3D sample in the atomic level can affect the properties in the bulk level, in the bulk properties. That means resistivity and conductivity are material properties. So if there are vacancies present in this material, these properties will be affected, and we are the affected properties, we are utilizing these affected properties to calculate the number of vacancies in the material. This is what this theory of concentration measurement of vacancy is. Then just to introduce you to another, we discussed about the vacancy defect. We know about the impurity, like introducing one impurity element into the material. This is known as impurity defects. Then we will be talking about the defects which we discussed earlier, such as ionic solids, that is Frenkel defect and Schottky defect. There is another one defect called self-interstitial defect. Self-interstitial defect, as you can see, the name suggests that there is an interstitial atom. Interstitial, you mean there is a interstitial atom is in, it means that there is an atom which is present at the at the sites, at the not non-lattice sites. That is known as an interstitial atom. And there is a term called self. That means within the material or within the crystal structure, um, there is an atom which is missing, and this atom is sitting at at a different position other than the lattice site. This is known as self-interstitial defect. Like there is a creation of vacancy, and this atom which is vacating here is sitting in different position. This is known as a self-interstitial. Self-interstitial. Within the same material, there is an interstitial defect. As you can here see here, sorry, there is a vacancy created here, and this material, this element is, this atom is going and sitting at a different place. Then there is one more defect called Frenkel defect. The Frenkel defect, as I told you, is in ionic solids. And ionic solids, by definition, has two charges. One is positive charge, one is negative charge. And the overall charge of the atom of the material is neutral. the same number of positive charges and the same number of negative charges. So before I talked about atoms, small atoms in whole, they are present. But let's see what happens in case of ionic solids. We have a video regarding Frankel defects. Let's see what is happening. These are the lattice. These are the crystal lattices, ionic crystal lattices containing positive and negative ions, as you can see here.
Frankel defect arises in the ionic crystal due to the large difference in size of the constituent ions. In such defect, the smaller ions dislocate from its normal lattice site to an interstitial site, creating a vacancy defect at its original site and an interstitial defect at its new location. Frankel defect is also called dislocation defect.
So yeah, you got to know what is Frankel defect. That means the cations. There are two types: anions and cations. Anions are those elements which are generated, which are like the negative charged elements. The cations are the positively charged elements. So that means, as you can see here in this figure, the negatively charged elements and positively charged elements are present. And the in Frankel defects, these cations, that is the positively charged elements, sit at a different site. This is the original site of the atom. It goes and sits in a different site. As you can see, as you saw in the self interstitial defect, there was a vacancy created, and this atom goes and sits in a different site. This same happens in case of ionic solids. These were neutral solids. This same happens in case of ionic solids. That's why we are giving a different name to that. The that is the cation sits in a different place. So there is a vacancy of a vacancy in this area where the cation is not present, and there is a interstitial created where the vacancy, where this cation goes and sits. Similarly, what happens, somebody can say that, okay, the cations are going and sitting in these different places, so there may be an option that the anions are also moving and going and sitting and going and sitting in a different place. Of course, there is a possibility of that. If the anions go and sit in a different place, there will be a creation of vacancy here, and there will be a creation of interstitial defect in the other place. But the term for this is anti-Frankel defect, because the Frankel defect is only related to the cations. We are only considering cations, the positively charged particles going to a different location. So when the negatively charged particles go and sit in a different way, we just call it anti-Frankel. So more about this can be discussed. We'll be discussing in the further lectures. So these Frankel defects, these interstitial defect, self-interstitial defects, the fraction of the defects which are present can also be found out with the help of thermodynamics. And the problems related to these defects, we'll be doing it in the next couple of lectures. So if you have any doubts, you can ask me in this presentation, or we can go ahead and end this lecture for today. If there are no doubts, then we can end this lecture. The lectures are even recorded, so we can go look into that again also. I think there are no doubts, so it's better to end the lecture. So we'll be meeting in the next week at the same time. If we have any doubts, we can just clarify those doubts in this class.